Hi, my name is Alisa, and I'm a freshman looking to concentrate in computer science.
Hi, my name is Lee, and I'm a junior concentrating in applied math with a secondary in computer science.
Hi, my name is Joy. I'm a freshman looking to concentrate in computer science.
And our project is Mirroring Music, music generation with hidden Markov models.
While researching machine learning algorithms, hidden Markov models stood out to us the most. Then, as the three of us were looking at applications of hidden Markov models, we decided to go with something we are interested in, music. Out of the many applications within music, such as contour processing, sound detection, and beat tracking, we decided to focus on music generation.
So first, a little explanation about what our chosen data structure is, the hidden Markov model. Hidden Markov models are a type of statistical Markov model in which the system being modeled is assumed to be a Markov process with unobserved or hidden states. To break that definition down, we will firstly look at what a Markov model is, and secondly, what they mean by hidden states. In statistical terms, a Markov chain is a graphical model. So that's one that describes the relationship between nodes, which in this case are musical notes. A characteristic of a classical Markov model is that each state is only dependent on the state immediately preceding it. For our model, this would mean that the probability of going to, say, a B flat is only dependent on the node immediately before. Our first implementation of the model used this classic model. What we described as an order 2 model, since two nodes are involved. We found ultimately that a modified order 3 version, in which each state is dependent on the set of two notes preceding it, produced melodies more similar to our general perception of tonal music. Because our chosen training data, which we used to gather transition probabilities between states, was through composed, meaning there was a single melody with no discernible sections, our hidden states were not particularly useful. These hidden states represent larger states like the chorus or the verse in music, which themselves can transition between each other and can produce notes with different probabilities. Our implementation allows for up to 3 hidden states. Currently, only one is used, with 100% probability that it will stay in that single hidden state. However, one could, for instance, mimic a melody in sonata allegro form, where the 3 parts, namely the exposition, the development, and the recapitulation, would each have their own set of order 3 note transition probabilities. This was not done for our implementation since there is no reliable automatic way in which to read in transition probabilities between hidden states. Marking where exposition ends and development begins, for example, would have to be done by hand. However, the capability is entirely implemented here. In terms of how we stored our transition matrix, we chose to use a 3D Python dictionary rather than a traditional 3D 12 by 12 by 12 matrix, which would have been sparse considering our fairly limited training data, and thus a waste of space.
There are 3 major steps to our project. The first step is fetching the music. We were able to use Music21, a package created by MIT, to read in MIDI files and translate it into an array of notes which have the properties of pitch and duration. The second step is processing the music. First, a transition matrix named Count2 is created based on the probability one note of a specific pitch will be followed by another. Second, a transition matrix named Count3 is created based on the probability a set of 2 notes will be followed by another. Finally, a transition matrix named Count_d is created based on the probability one note of a specific duration will be followed by another. The final step is generating the music. This is done by generating a random starting pitch and duration, which in turn will determine the key of the piece. The pitch of the second note will be stochastically determined based on count 2, but all the other notes thereafter will be determined based on count 3. All durations will be stochastically determined based on count t. This is an example of one of the pieces that can be generated using our program.
Of our original goals, we succeeded in implementing all 3. Our original goals were to 1. Fetch the music by reading in MIDI files, 2. To process the music by creating Markov chains built on transition matrices, and 3. To generate new music based on the Markov models. Building upon that, we proceeded to implement an order 3 model with extra features, such as a separate Markov chain for note durations. Our project here is only a step towards music generation. If given more time, we can expand upon it by implementing higher-order Markov chains, as well as selecting a wider range of training data that incorporate Western classical chord progression and a more practical application of hidden states. Thank you for listening to our project.
And we hope you rock out with our new tunes.